Creepy. Okay, guys, so we've got the solutions we were doing last time. I think we ended on talking about some problem-solving techniques for solutions. Am I correct on that? So looking at converting between different kinds of units and solutions. Anyone want to weigh in on that?
Yeah, the last thing I have is molality to
Solubility.
solubility, yeah.
Okay, cool. Okay, perfect. So the last things that we need to talk about are what are called colligative properties. So colligative properties are properties that the value only depends on the number of particles in solution, not what they are, okay? So I'm not sure if you guys remember back to chapter 4, but we did a lot with trying to figure out the concentration of ions in solution. You guys remember this, especially from the and that was definitely one of the things that I saw you guys struggling with, but this is why we worry about the concentration of ions, right? We want to know how many particles are in a solution, not just the concentration of the molecular substance, right? So when we talk about ionic solids especially, ionic solids, the molecular concentration or the concentration for each formula unit is not necessarily the concentration of the ions present. Does that make sense? Yeah? This is super important. So if you guys don't understand what I'm saying, we should talk about it. So how about I give you a little example? So if we had, let's say, a 1 molar solution of aluminum chloride. Whoa. Right? What would the molarity of ions be?
Would it be 1 molar?
So how many ions do we get when we dissociate this guy?
4.
Be 4 ions.
Yeah, we get 4 ions, which means that the concentration of ions, 4 molar. Now, is it exactly 4 molar? No, because not all of these are breaking up completely, right? You get this thing that can happen where you can form what are called ion pairs, where some of these things are technically dissociated, but they're still kind of stuck together. So would this technically be the concentration? No, it's a little bit off, but it's good enough, okay? Does that make sense though? Cool. Everybody okay with that? So colligative properties aren't just determined by what your solution contains, right? But how many particles it contains, right? So especially for ionic solids, this is going to make a big difference, right? Coolsies? I was trying to go to the chat. Cool, thanks, Harrison. All right, cool. So let's look at some examples of these properties. So vapor pressure is one of them. So when we talk about, so what we were talking about in chapter 10 was the vapor pressure of a liquid, right? So we're talking about pure substances in that case, right? Now we're talking about the vapor pressure of solutions, right? So how does the interplay between the solvent and the solute change the vapor pressure, right? So when you have solute particles placed, replacing some of the solvent molecules, then that's going to change the amount of vapor that you can have above that liquid, okay? So specifically, if we were looking at ions in solution, do you think that would increase the vapor pressure or decrease the vapor pressure? So when we talk about vapor pressure, sorry, Kevin, I'll let you finish in just a second. When we talk about vapor pressure, we're always thinking about the intermolecular forces, right? So adding ions into, let's say, water, right? Is that going to increase or decrease the intermolecular forces?
Increase,
Why?
because ion dipole is stronger than hydrogen bonds.
Exactly. Does everybody understand that? We're tracking live? So if the intermolecular forces are increasing, what's happening to the vapor pressure?
It's going to increase, or sorry, it's going to decrease.
It's going to decrease. Does that make sense, guys?
It's going to want to stay in liquid form because the bonds are, or the forces are stronger.
Exactly, right? So the ion interactions with the solvent in this case are actually increasing the interactions, the intermolecular forces, right? Because the ion pull on those water is strong. So what ends up happening is you reduce the vapor pressure when you add an ionic solid, generally, not always, right? There are some ionic solids that are not going to interact with water as strongly. But as a general rule, that's kind of what's happening here. Cool. And the process of making a solution is going to disrupt this vapor liquid equilibrium that exists, right? So you guys remember we were talking about this equilibrium that exists where you have the rate of vaporization and condensation are equal. Right? It's not about the amount of molecules that are in the vapor phase or the amount of molecules that are in the liquid phase, but it's just that the rate of evaporation, aka molecules going into the vapor state, is equal to the rate of molecules going into the condensation phase, right? So this process essentially looks like a steady state where nothing's changing. The pressure is not changing, the volumes aren't changing, etc. Does that make sense, guys? Everybody all right with me? Cool. So again, adding that ionic solid is going to make this equilibrium shift, right? Specifically, it's going to make condensation increase until they come back to equilibrium, right? And once they come back to equilibrium, there'll be a lower vapor pressure above the liquid. Yeah, that's the picture. Does that make more sense with the picture? We all right? Are you guys totally zoned out? You don't want to talk to me anymore?
So the red's just a solute?
Exactly. That's exactly right. Cool. Brooke, Brittany, Jerica, Rashilda, you guys okay with that? Making sense?
Yes.
Cool. And so again, that equilibrium will always be reestablished, right? If we give it enough time. And in this case, when we reestablish the equilibrium, there's less molecules in the vapor phase, right? So the vapor pressure will be lower. So this relationship between the vapor pressure of a solution and the vapor pressure of the solvent by itself is governed by what's called Reults Law. And so the vapor pressure of a volatile solvent above a solution is equal to its normal vapor pressure, that's this guy, right? Multiplied by its mole fraction in the solution, right? So this is talking about the mole fraction of the solvent, okay? because the mole fraction is always less than 1, the vapor pressure of the solvent in the solution will always be less than the vapor pressure of the pure solvent, okay? That was a lot. I don't think it's super helpful to solve problems with Reults Law. I think there might be some in the homework, but I'm more interested in you guys understanding this, right? So for me, understanding this picture of what's happening here and how the vapor pressure is reduced by adding a non-volatile solute is what I want you to take away from this. Okay. So vapor pressure lowering. The vapor pressure of a solvent in a solution is always lower than the vapor pressure of the pure solvent, okay? Now, this is true when you have a solute that is non-volatile, right? The vapor pressure will always be lower. What do I mean by a solute that's non-volatile? What does that mean? So when we talk about volatility in a liquid, what are we talking about? Not about reactivity.
Does it have to do with like the phase?
It does, yeah. So when we have less intermolecular forces in a liquid, right, then that liquid is easier to vaporize, right? So a liquid that's easier to vaporize has a lower, has a higher vapor pressure, meaning there's more of the molecules that are going to exist in the vapor state because it's just easier to get them into that vapor state, right? So if we think about, remember the kinetic energy curve for the molecules, when we're looking at a liquid, the average temperature is not the temperature of every single molecule, right? So the number of molecules that would be able to get over the threshold in a volatile liquid would be higher than in a non-volatile liquid. Right? Does that make sense?
Can you say that one more time?
Yes. So for example, a volatile liquid would be something like, and it's not super volatile, but relatively speaking, volatile compared to water, would be something like ethanol, right? Ethanol evaporates more quickly, would have higher vapor pressure, right? Has lower intermolecular forces, right? That's all a property of a volatile liquid, right? Does that make sense?
Yeah, I just got lost at why does ethanol have a higher vapor pressure if it boils easier at a lower temperature?
Because we're talking about, yes. So when you say volatility, you mean ability to vaporize. Yeah, exactly. Right. So I know that that's kind of counterintuitive, right? But the vapor pressure above a liquid that has less intermolecular forces will always be higher, right?
Yeah.
Because it's easier to get it to go into that vapor phase.
Right. I just got confused.
No, that's okay. That's why we talk about this stuff. So it's very easy to get confused. Okay, so come on. So this is the Reults Law for a volatile salt. So this would be, let's say we had water and we added ethanol to it, right? If we had a cup of pure water sitting next to a cup of vodka, right? Which one's going to evaporate quicker?
Vodka.
Vodka, right? So that's what we're talking about here, right? Is the addition of a volatile solute to an otherwise non-volatile solvent, right, will actually make the vapor pressure increase when we're talking about a more volatile solute. Does that make sense, guys? And then just like for gases, there's ideal versus non-ideal solutions. We're not going to get too deep into this, but I just want to show you these curves because I think it helps you kind of make sense of things. So when you're talking about the vapor pressure of the pure substance, and then we're talking about the mole fraction, I'm sorry, I think the pure substance is over here. Right, so the ideal solution would have this kind of linear behavior between the partial pressures of each one of those components. So again, going back to our vodka example, right? We'd have a partial pressure for ethanol in that solution, and then we'd also have a partial pressure of water in that solution, right? And then we have the overall vapor pressure is related to how much of each of those components is in the solution, right? AKA the mole fraction. Does that make sense, guys? Kind of, sort of, kind of.
Yeah, that makes sense.
Cool. If we're looking at strong solute-solvent interactions, right, we actually depress the vapor pressure, right? So we take it away from that ideal condition because now the interactions between the solute and the solvent are stronger than the solvent and the solvent, right? That makes the vapor pressure lower. In terms of weak solute-solvent interactions, or another way of saying that would be the intermolecular forces in the solute are smaller than the intermolecular forces in the solvent, right? This is where you get that increase in vapor pressure, right? Because you're adding something that's more volatile. Is this making sense, guys?
Yes.
So let's ask a question. If you have a beaker sitting out, same size beaker, two of them, and we have in one beaker, we have water, and in the other beaker, we have salt water. Which one will evaporate more quickly?
Just regular water.
Regular water. Does that make sense, guys? Does this make sense biologically in terms of our planet? So our largest body of water is the ocean, right? And it's pretty salty. Is this beneficial for us? Yeah, right? It would be a lot easier to evaporate all of that water if there wasn't a bunch of, bye Harrison, a bunch of salt in there, right? So I think hopefully there's a little bit of intuitiveness about this. But is everybody picking up what I'm laying down here?
Yeah, I understand that part. Can you repeat? So you said if you add a volatile solute to a non-volatile solvent, that's gonna increase the overall vapor pressure?
Mm-hmm. Yeah.
Okay. So what do you mean by weak solute here? Does that mean non-volatile or volatile?
Volatile. So when we're talking about strong solute-solvent interactions, right? This would be something like an ion-dipole interaction.
Okay.
Right?
Why is the vapor pressure going down?
The vapor pressure goes down when the solute-solvent interactions are really strong, because now the molecules are being stuck together more tightly, right? So even though the same liquid at the same temperature would normally have a vapor pressure that's higher, now those molecules are being held onto more tightly, right? And so so there will be less of the molecules that are able to go into that vapor state. Does that make sense?
Yeah, that's like the example of like salt water, right?
Exactly, right? So this guy would be something like adding salt to water, right? This guy would be something like adding ethanol.
I wasn't interpreting the graph correctly. I didn't see like the dashed line is where it should be, and then okay.
Yeah, so this is the ideal behavior, right? Where there's no change. And this is the actual behavior based on these different types of solute-solvent interactions, right? So the ideal solution can't account for this idea of solvent-solute interactions, right? Especially because those solvent-solute interactions are going to be different for every solute solvent, right? So that's what we're saying here, right? In the same way that the ideal gas law can't take into account the intermolecular forces or the attraction of particles, right? The ideal solutions can't do that either. Does that make sense?
Mm-hmm.
Cool. Mainly what I want you guys to take away from this is this idea of solvent interactions, right? Are they increasing? Are they decreasing? If the solvent-solute interactions are increasing, then it means the vapor pressure is going to decrease, right? And vice versa. Cool. So the next colligative property that we have to talk about is, okay, cool, we've got time, is freezing point depression and boiling point elevation. So we live in a place where freezing point depression is not really something that we deal with a lot, but people that live in snowy places know a lot about this, or at least understand it to a certain degree. So freezing point depression, if you have a solvent like water and you add something to it that has stronger intermolecular forces, you can actually make the freezing point go down, right? So for example, if we're talking about trying to make the freezing point of water go down, then we can add salts to the road to make sure that they don't freeze, right? So in places where it snows a lot, they'll often salt the roads. Have you guys heard of this? No? Anybody from a place?
I've heard of it.
What was that, Brooke?
I've heard of that.
Okay. And that's why they salt the roads, though, right? So this idea of solvent-solute interactions also goes into the freezing point and the boiling point. Okay, so this is one of the things that you'll definitely have calculations with on the exam. Freezing point of a solution is lower than the freezing point of the pure solvent, right? Specifically here, we're usually talking about an ionic solvent, an ionic solute, right? And so we have the freezing point of the solvent, the pure solvent, and that's subtracted from the, and the freezing point of the solution is subtracted from that. That gives us this delta T of freezing, which is the change in the freezing point, right? This K is called the freezing point depression constant. There's tables with those. Most of the time when we're doing problem solving, we're probably just going to be using water, and that will always be given to you. Okay, what does little m stand for?
Molality.
Molality, right? So this is good old-fashioned molality. Now, again, we're talking about colligative properties. So is this the molality of the solution or the molality of the ions?
The ions?
The ions, right? So colligative property is something that depends on the concentration of particles, right? Not just the molecules that are there, right? We want to know specifically how many of the particles are in solution, right? So something that has more ions would have a greater effect on the freezing point than something that has less, right? Does that make sense, guys?
Could we do an example of something like this?
Yeah, absolutely. And there's some in the homework as well, but I just want to go through and make sure that we cover all the material first. Probably we'll be able to cover that on Thursday at the beginning.
Okay, no problem.
But they're actually pretty straightforward questions, right? The hardest part is being able to calculate the molality, right? Other than that, it's kind of a plug and chug deal, because usually you're not even looking for the actual freezing points, right? You're just looking for the change in temperature, right? So how much did it decrease? Does that make sense?
Yeah.
Cool. And then, so these are some of the KFs and KBs. So the K for freezing, right? So we've got water is 1.86. Again, that's the one that we're going to use most often. But you'll see some of the problems in the homework will use different solvents, right? So you may have to use a different K. But again, they're just they're just things that you would look up in a table. Okay, bye. And then the boiling point elevation is the same concept, right? But if you'll notice here, the boiling point of the solution is first, the boiling point of the solvent is second, right? The idea here is because we're trying to get a positive number for the delta T, okay? That's why those are flipped. But it is important when you're trying to solve for the new boiling point of a solution, okay? Does this make sense, guys? So is this a large effect in terms of the boiling point elevation in ions? What do you think? What do you figure the molality of your pasta water is when you're making pasta? Give it a guess. I'm gonna make you guys guess. Nobody? Nobody's ever boiled water to make pasta?
Well, you said the molality?
Yeah, ish. I mean, just off the top of your head. You don't have a lot of experience with molality, but just guess.
As like just as far as water?
Mhm.
Using water?
Yeah, so like tap water.
Would it be 3?
Do you think it would be greater than 1 or less than 1?
Oh. I'm thinking of the ions, like breaking apart the ions.
Mm-hmm. Yeah, but even in tap water, right? There's not, I mean, there are more ions than distilled water for sure, right? But is tap water like extremely conductive?
Not really.
Not really, right? So I would say that, and I'm totally making up these numbers, but I would say if I had to guess the molality of tap water, maybe 0.05 mole. That one's really hard to say. That's a pretty freaking small number, right? And if we look at KB for water, right? 0.5 times 0.05, is that going to make a dent in the boiling point of water very much? It's pretty small effect, right? You guys picking up what I'm laying down here?
Kind of.
You want me to write them out? So
If you want.
this is kind of an important one for you guys to understand. So let's say we have a molality of water that's equal to 0.05 moles per kilogram. Oops. And we have our KB of water is 0.51, right? So plugging those two into this equation, right? What does that give us for the change in boiling point?
Like when you multiply them together,
Yeah, exactly.
it gets smaller
Yeah,
than
so
molality.
you end up a TB, right? Which is less than 1 degree. Does that make sense? So the molar concentration of a solution that you would have to really change the boiling point is kind of a lot, right? Does that make sense, guys?
Yeah, that
Yeah, no,
makes
that
more
makes
sense.
sense.
Cool.
Visual.
Yeah, I always think it's helpful to have examples. Ugh. Now, if I can only undo them. Thank you. Something I do when I'm putting on the text makes it so that I don't have a mouse. It's really hard to get the mouse back. Sorry, guys. Okay, cool. So that's what we're saying. So in terms of effect size, right? Just looking at the KB and the KF, right? The KF for water, this freezing point constant, is a lot bigger than KB, right? So a smaller molality will lead to a larger freezing point depression than it will boiling point depression, at least in the case of water. It looks relatively similar amongst other solvents as well. Does that make sense though, guys? You picking up what I'm laying down?
Yeah, that makes sense.
Cool. Okay, so then the last one, I believe it's the last one, is osmosis. So this is the process of a solvent flowing across a semi-permeable membrane from low concentration to high concentration. So I think this makes a lot more sense with a picture. So if we're talking about, if we're talking about a solution over here and pure water over here, right? What's going to happen is the solvent is going to want to flow this way, right? It's going to want to flow this way to try and lessen the concentration gradient. Does that make sense?
Yes.
So water moves towards higher solute concentration.
Exactly. Yeah, to try and level the playing field, as it were, right? Now, where would you find a biological example of something like this? A semi-permeable membrane.
Your
Plasma membrane?
body.
Yeah, how about cells, right? Cells are basically contained in semi-permeable membranes, right? And a lot of the action that happens in the cell is determined by the concentration of ions in the cell, right? This is also why you shouldn't ever drink distilled water, right? If you drink distilled water, what's happening is you're increasing the amount of solvent outside of all of your cells, right? And what that's going to do is pull more water into your cells, right? AKA make you get more bloated. And then the cells can explode if you do too much of that, right? If you have something where it's the opposite, let's say instead of having a pure solvent here, we had a more concentrated solution, right? Then the water molecules would flow the other direction. Does that make sense, guys? We cool?
Yep.
Cool. And so this ability to go against the force of gravity is what's known as osmotic pressure, right? So this is a pressure that can build up because the force of osmosis trying to level out this concentration gradient is strong enough that it's able to create an osmotic pressure. Questions about that? That's really about as much as I need you guys to know. If you guys are bio people, you'll look way more into osmosis, but I don't usually do too much with osmotic pressure in terms of calculations. But even if we did, I mean, it's pretty straightforward, right? You're literally just looking, this is the osmotic pressure, molarity, R, this is the R value that you're using, and T, right? So it's not a super complicated calculation, but I also don't think it's super relevant, so I probably won't ask you any. Okay, so the Van Hoff factor is the ratio of moles of solute particles to moles of formula units dissolved. I think I mentioned this just a second ago, but when you have ions dissolved, right? Even if the entire solute is dissolved, it doesn't mean that all of it is in ions, right? And so the Van Hoff factor tells you essentially is if you're looking at the expected Van Hoff factor, then that would be how many particles you would expect in solution if there were no ion pairs, right? The measured Van Hoff factor is what you actually get when you measure the conductivity, right? So the conductivity is reduced slightly because of this ion pairing effect, all right? Does that make sense, guys?
Yeah.
Cool. Now, functionally speaking, I like you guys to understand that the Van Hoff factor is not actually going to be the expected, but in terms of what I have you guys use, I'm not going to ask you to use the actual Van Hoff factors. I'll just ask you to use the expected, right? So just looking at these expected, right? The expected Van Hoff factor I for NaCl is 2, right? Why would that be?
Because there's 2 ions that dissociate.
Exactly, exactly. Does that make sense, guys? And here we'd have 3 ions. Here we have 4 ions, right? So the more ions you get in solution, the lower the Van Hoff factor usually gets, the actual Van Hoff factor. But again, I don't really need you to know that. I just want you to know the expected, which would be that if you have a non-electrolyte, aka something that's not going to dissociate, then the Van Hoff factor is just 1, right? So the concentration of the solution is the concentration of the particles. But the Van Hoff factor for any ionic solid will just be equal to the number of ions that are formed from that ionic solid dissolving. Does that make sense?
Yes.
Cool. Oh, that was a very poorly placed slide, but the Van Hoff factor is really more relevant when you're talking about colligative properties like freezing point depression and boiling point elevation, right? So technically this equation that we have should be molality times I, right? AKA the molality of the ions. Does that make sense, guys? You want me to write it down?
If possible, yes. So molality times
Yeah,
the
so
Van Hoff factor.
technically, so annoying that my my shortcuts don't work. So it should be delta T is equal to I times times the molality times kV, right? Or the molality of the ions times kV. Does that make sense? They're saying the same things. So if we're looking at the molality of the ions, right, then this M times kV is fine. But if we're looking at the molality of the solution, then we need to multiply in I. Quit. Does that make sense?
Yeah, that makes sense.
Cool. I just like to point out that I is related to this, right? But if you think of the molality here as just being the molality of the ions in the first place, then you should be fine. Okay. Give me back my mouse. This is totally why I never I never do the annotation feature, because it takes away the mouse. It's very annoying. Okay, cool. All right. So that's going to be on all of our slides from now on. Cool. Okay, so this osmotic pressure, right, is something that we can see in terms of cell behaviors. So we have isoosmotic, or this is sometimes called isotonic. Cell concentrations are similar to the outside liquid concentration. We can have hyperosmotic. Hyperosmotic is when you have much higher concentration of ions outside of the cells. The water is essentially sucked out of the cells by osmosis, right? So this would be why you don't drink seawater, right? And then the last one would be hypoosmotic, where you have the cells are inflating because there's a lower concentration outside the cell than there is inside the cell. Does that make sense, guys?
That makes sense.
Cool. All right. I'm just going to briefly talk about suspensions because they're kind of cool. So we've been talking about solutions, which are always going to be homogeneous, but you can have suspensions, which are somewhere in between a homogeneous and a heterogeneous solution. Basically, you have, or rather, somewhere between a homogeneous mixture and a heterogeneous mixture. The heterogeneous mixture being suspended is basically making it look like they're homogeneous. So examples of those would be aerosols, which would be a liquid suspended in a gas. Fog would be an example of that. Solid aerosol would be a solid suspended in a gas. Example of that would be smoke. Foam would be a gas suspended in a liquid with cream. An emulsion would be a liquid suspended in another liquid. So milk would be an example of this. Also, salad dressings often will have emulsifying agents in them. And then the solid emulsion, it has opal there, but I think probably gelatin is a better example, right? So gelatin has liquids suspended in a solid. And we're good. Questions? We lost people. I know, I'm a little over time. Sorry, guys.
So as far as osmotic pressure, you were mentioning, just know the relationships of like where water moves in different conditions.
Yeah, essentially what I want you to understand is just the driving force there, right? So if you have a concentration gradient, the low concentration will always flow towards high concentration to try and right the ship, right? In the same way that temperature always flows from high to low until you get rid of a temperature gradient.
Got it. Thank you.
Mm-hmm. Other questions, guys?